of discovery, then we'll kind of focus on that. And what we're going to focus on, and what my main topic of research has been, is linear predictive models and supervised learning. So if we are in the feature space, we have, for example, this classification problem with 4 points, 2 green, 2 purple, and we want to make a line to classify them. And that line is parameterized by a weight vector. And we find that weight vector by solving an optimization problem, and we maximize the goodness of fit based on assumptions. And assumptions is the key word here, and we're going to cover that quite in depth. And we can use either primal or dual techniques. It doesn't matter as long as they're linear, because we can always look at the weight vector in the feature space. So what exactly is that weight vector W? So its goal is really to make a prediction about a new data point, so X star in this case. So if I take my brain with, let's say, only 2 voxels, and I fit in my model, and I have weights for feature 1 and feature 2, then I get my new example, and what I do is I multiply the weight of voxel 1 by its value. I do the same for voxel 2. I add everything together. We've assumed a bias of 0, and we obtain a number. And that number is either the regression value, or if it's a classification problem, if it's positive, it's going to be attributed class 1. So typically, that's just how it works, and what that weight vector is really aimed for. We can project the weight vector into feature space, which makes this nice heat map in the shape of a brain. It does represent the contribution of each voxel to that then really big function here, because we have hundreds of thousands of voxels. What it is not is a statistical parametric map. It means we can't do any local inference. And that's a limitation for discovery. But it's very important to stress out why we can't make local inferences. So when I see that map, it's actually a map of faces versus houses in the Haxby dataset. So what I really want to do, the first thing I want to do is I want to do that, and I want to just look at the very bright red parts and the very dark blue parts and kind of ignore whatever is in between. So it's very tempting to threshold. But if I threshold, what I'm doing is it's a bit like looking at only the top voters or the loudest speakers on Twitter. We know they don't represent the overall. If you were to have an election tomorrow, you just take the votes from people that you hear about on Twitter, and you take the vote from the general population, you're going to have 2 very different results. And here, the thing is the same. If you're only looking at those very high contributions, you actually don't get the full story, because you've actually set all of, like, quite a large portion of your weights to 0. And that is a different function. So that actually does not represent your classifier anymore. So the accuracy, PAR-AUT or RC, area under the curve, that you obtained from the classifier you've estimated, as soon as you threshold your wet map, those numbers do not correspond to that thresholded map. So they're different models. Now, also, what is in the amplitude of waste? So let's say you're not thresholding. You have a small number of features, you're not thresholding. Does that mean that the feature with the highest contribution also has a direct correlation with my signal of interest? If we take a very illustrative example, we have Y, which is our signal of interest, and 2 features. First feature is Y plus some noise. The second feature is just the noise. Now, if we take a model that predicts Y, if it was smart, what it would do is just give a weight of 1 to feature 1 and a weight of -1 to feature 2, so that you eliminate the noise. And this was discussed quite in length in this paper by Schrouff et al. In 2014. And it shows that machine learning techniques will harness a noise cancellation process when they make their decision. And so this is a very illustrative example. It is like, yeah, it's just illustrative. I was not completely in agreement with it when I read it, but it does show, and that also appears in the data. So we also have a lot of examples where the top weights actually agree with the literature. So how about those? Like, is it just like, no, we can never look at weight maps, or that amplitude never means anything in terms of brain signal, or are there more parameters out there? So if we take that, an example that I mentioned earlier, and you do a very simple thing, you do an SVM classifier, and what you do is you take the weights and you map them to the AAL atlas, and you just summarize the weights into each of the regions. And then you sort the regions according to that average weight that you obtain. And what you see is you have at the top, you have fusiform, left, and right. And that kind of makes sense. Like, this is something we would expect. But you see also that this is a long distribution with a really heavy tail. But still, we kind of want to assess when could I trust it, when could I not. And for this, we did a small experiment where we would vary the signal-to-noise ratio and the sparsity in some simulated data. So in this case, it was not neuroimaging, it was intracranial EEG. And I had, just because it's easier to see and more manageable in terms of dimensions as well. But I had rest data, and I just added randomly windows of conditions A and of condition B. And then for condition A, I added some step signal in the high-frequency broadband. And for B, I did not. And I varied the amplitude of that step to vary the signal-to-noise ratio. And I also varied the number of channels that I would add that signal on. And I would vary the sparsity. And then I compared the weight maps that I obtained from the machine learning to that ground signal that I input, because I know that that's there. And the rest, like the actual resting activity, is considered as correlated noise. So if we look at the signal, that's what it looks like. That like conditions A and B before I add the step, and that's what it looks like after. And I used two techniques. I used SVM, and I looked at the feature level and at the channel level by just this averaging procedure that I mentioned earlier. But I also looked at multiple kernel learning, because multiple kernel learning is actually an L1 regularized technique. So that means that it enforces sparsity. But the way it does that, it does not do it at the feature level. It does it at the kernel level. And so if I look at my different channels, so this is another example, it's mat and non-mat instead of A and B, but this actually applies, like it's the same concept here. So you have your different channels, and for each channel, across the time steps, you build a kernel, and then you estimate a classifier, and you build your final classifier as a weighted sum of those little small classifiers, and you have an L1 on this term here, on this contribution of each channel. So it's going to push some channels to not contribute at all, so no time step at all, and others will have a contribution. And this is, of course, optimization process, so that feeds back into here, and so on, until it's convergence. And so what we observe is, if we look, so these are the SVM weights, we actually see that So in blue, this is the signal of interest. That's the effective signal of interest. And in gray, it's the signal that I input, that step. And in orange, it's the weights. So we see that the weights actually follow those, that noisy signal that was present in the data. And we see it for different signal-to-noise ratios. And yes, it does not completely follow the steps, but it's still fairly close to the actual signal that we know is in the data. And now if we look at the cosine similarity between the weight and the signal, if we concatenate all the weights across all the channels and time points, so for SVM, what we see is at the feature level, we vary the sparsity, we vary the signal-to-noise ratio, and we see that the cosine similarity is better in like this area here, where you have a high signal-to-noise ratio, and also the signal is more distributed. And SVM is an L2 regularized, so it means that it's going to push some weights to be close to zero, but they will never really reach zero. So all of the channels will have some contributions to the model for SVM. Now, for MKL, we see the pattern is different, and we see that actually the cosine similarity is bigger in this area here, where also we have higher signal-to-noise ratio, but the sparsity is actually better represented in the signal. And it's really similar if we look at the channel level for SVM and for MKL. So overall, we see that at the channel level, when we average, we get higher cosine similarity in all cases. And we see these patterns that actually represent the hypothesis, the assumption that we made when we chose either SVM or MKL. And so that shows that you really can see your hypothesis being represented in your weights and in how your weights behave compared to your input signal. And now for the averaging part, if I had averaged or performed the MKL on time steps instead of channels, the results would be completely different. Actually, the result would be, everything would be the same because there are no differences across time points, although they are across different channels. And so like this increase, it just reflects the fact that I know I should average across channels compared to just in all situations you should average across channels. If that makes sense. And so the other important things we wanted to look at were the true positives and the false positive rates. So that means how many times was a channel on which we added signal actually had a contribution to the model, and how many times for a channel on which we did not input signal did it contribute to the model. And we did for SVM, and as I mentioned, SVM actually gives weight to everything, so it's not as relevant. But we see that there are some areas here where we don't have all the true positives. It just gives weight to other channels. It prefers to cancel some noise rather than just adding more channels which have the same data, because that step is the same for all channels. So it's correlated signal. And if we look at MKL, it's also what we were expecting because MKL is sparse, so that list is going to shrink as soon as we get into more distributed signal. And so that the number of true positive is going to be very small for MKL. Now, the false positives, we see that for SVM they are important, and that's because SVM distributes the weight. For MKL, they're less of a problem, especially if you are in this high signal-to-noise ratio area. If you're not, then again, it's going to depend on whether your signal is sparse or not, and whether that would be a fair assumption to make on your data. And the last thing is looking not only at just the false positives overall, but at the false positives in the top 10, which is a very arbitrary threshold, but that is often used in the publications. And for that, the pattern in SVM is quite different, but we see still that same pattern where for low signal-to-noise ratio, they are false positives, and especially that holds even for high signal-to-noise ratio, but if your signal is very sparse. And for MKL, the pattern doesn't change that much, which just because MKL is sparse, and the top 10 is actually very similar to the overall list. So that shows that the weight amplitude, it depends on the hypothesis, on the signal-to-noise ratio, and on the sparsity. It's not a clean, no, you can never look at your weight, or, oh yeah, that's fine, I have high signal-to-noise ratio, I'm just going to look at them, they should be okay. So it's really hard to assess those properties from your data to start with, but when you make an assumption, when you choose a classifier or a regression machine, or any type of machine learning analysis, you actually make a choice, you make that assumption, and so you should be aware of that assumption you are making in terms of your signal distribution and on the properties of your signal as well. Now, another aspect was mentioned in this paper by Hubbard and Baker, who are here, and so that was whether weights would actually reflect the signal if there was covariance between the variables, and we actually show they actually show that they don't. And even worse, in the case that you have the noise covariance that depends on the classes, what you can have is that there are no differences between the mean of your signals, but if the covariances depends on the class, you might obtain that the accuracy does not even represent your signal. Now, this figure only represents if you look at total accuracy. If you were to look at class accuracies, which I highly recommend you do in any type of machine learning analysis, then you would see that for one class, the accuracy would be very low. And if you run permutations, then you would see that it would not be significant if you were to actually assess that classifier. So when I run a classifier, typically I run permutations not only on total accuracy, but on balanced accuracy and on class accuracies and on positive predictive values. And if all these measures are significant, then I can tell my classifier is significant. Otherwise, I don't. So that's why also looking at just a single metric is very dangerous. So to kind of conclude on weight amplitude, so you might have a high weight in a voxel due to an association between the voxel signal and the labels, which is the ideal situation, but also because of multivariate properties, such as correlated noise or signal. You can mitigate by having a high signal-to-noise ratio, but not in all cases. Now, a zero coefficient might be due to no association between the voxel signal and the label. So that would typically happen if you're using a sparse method, and the classifier or regression machine decided that this variable has no value. But it could also say, well, this variable, I already have that information in that other variable, so I'm not going to take both. So that's really just the choice of regularization that's going to impact that value. So if the goal is to make local inference about the association between underlying brain signal and the labels, then I'm not going to say don't use machine learning, but basically don't use machine learning, especially don't use only machine learning. I guess there are more techniques out there that are just better suited for that. If you want to do local inference, run an SPM. There are other types of analysis that can be run for local inference. But really, machine learning, you can just, if you want to be sure that your model has learned something that you think it should have, like faces versus houses, you want to see fusiform face area on top. Then you can look at the weights for that, but you should not rely on whatever weights you're seeing on top as being the main contributors of the brain signal in your problem.
What about searchlight applications?
Well, searchlight applications, they're very local by construct. So, yeah, so I'm not a super fan of searchlight because they're just looking at tiny neighborhoods. So they're not really harnessing any of the multivariate properties of machine learning.
But that's how you get localization.
So that's how you get whether a neighborhood of 9 or 16 voxels actually have any signal in your data. It's a quite expensive SPM, really. I think it can be used. I've never really found much use for them. The only thing that you need to be careful with when you use them is that you need to do correction for multiple comparisons. And that is not performed in the same way as you would do for an SPM. Actually, the way it's done for SPM would be would impose too many constraints. So you might have less results if you were to run those. But yeah, there are different ways to obtain the significance values. But yeah, you just need to pay attention to that if you were to run that. Okay, so now let's come back to this point about correlated noise. So as we've seen, if your correlated noise depends on your classes, so if the noise is correlated to your classes, whether you have a difference in mean between your signals from the different classes, this is basically a confound. This is what is referred to a confound. And it can be very tricky to make the difference between what you see a result of classification or regression that would be from a real difference between your signal of interest, or that would result from the confound. And they're really tightly entangled. And those confounds can be categorical, like a gender or a scanner, or they can be real values, like age. And having confounds or not might be an obvious problem, but sometimes it can be more difficult than that, because there are variables that we think might be confounds, like gender, but actually these might not be a confound. It might be that the pattern is different in males and females. And maybe we want to, instead of say that they come from all the same group, we actually want to harness that and explore that. So just very simple example where the noise is correlated with the labels. You record all of your patients from the hospital scanner, and you record all of your healthy subjects in the scanner from the research center. And data is very expensive, especially in neuroimaging, and that can happen. And I'm an author in this paper, so I can say it, but I have this example where actually we have patients and healthy controls that were recorded on 2 different scanners, and that's the target value. It's an anxiety score, and we see that typically the ones that were scanned on scanner 1 had lower target values, which meant lower anxiety, and the ones that had a higher target values were recorded from scanner 2. What that plot doesn't show is that there is an additional confound, which is that there were more females scanned on scanner 2 than they were on scanner 1, and conversely for males. That group is actually fairly small. So how to deal with that? So what's been done mostly is to apply a GLM and remove the confounding factors. Now, there are very efficient formulations and implementations of this operation, because you can apply it either in primal or in dual formulation, so you can do it directly from your kernel. Because you can do it from the kernel, you could extend that to nonlinear effects as well. Now, the important part is you need to do the correction within the train set, you obtain the parameters, and you apply them onto the test set. And that, again, is shown in this paper, how you can do that. But it's not necessarily a very common implementation of the correction, so just be careful. After you've done that, then typically what happens is that you're going to assume a single distribution. So before, you knew kind of that you had different distributions from your different confounds. So I have samples that are generated from scanner 1, samples that are generated from scanner 2, and then I remove this confound, scanner 1, scanner 2, removed it. Okay, fine, I'm just going to pull everything together in a big group, and I'm just going to run my classifier in it and forget about it. Now, the problem is that that single distribution assumption actually does not really hold. The first thing is DLM can remove the signal of interest. And we see it in this example I've just shown, where if you don't remove the confounds, you get significant, in this case, is the anxiety score, so it's a regression problem. So we get significant values for correlation between targets and predictions, R squared and mean squared error. But then we perform a linear GLM, and basically, well, that regression is not significant anymore. Now, to be completely honest, the effect is not super strong, so I'm not too surprised that it doesn't survive the correction. But still, it is a problem that is fairly common. If you remove your confounds, you can remove part or even a significant part of your signal of interest. And the fact that the unique distribution assumption doesn't really hold is actually, if you run permutations, you're going to run permutations as if all the points were then generated from that same distribution. So this pool that I put together after correcting. And if you do that, you obtain the blue distributions. So whether you correct so if you don't correct or if you correct. And that is for O squared or MSE for the same problem. But if now you perform the permutations by taking into account the structure of the groups, so saying, okay, I'm just going to permute labels between samples from scanner 1 and permute labels from only between the samples from scanner 2. So basically taking into account those confounds again, then you see a very different distribution, and that is way more conservative. So in this case, and even after you correct. So in this case, it's like what do we really correct for? We only take a bit of the signal out linearly, but we don't really consider the fact that they come from different distributions from the start. So one way to look at it that we investigated recently, and actually someone else who's taking that work over, so I'd be happy to pass your questions on if you have some. But one way we actually looked at was to consider distributions different, because they are. And what that implies is that we're going to make subgroups based on the confounds, and we're going to assume categorical confounds, as we have in this case. And we fit one model per distribution. And now what we do is we impose those models to learn something and to share something. So that they can have shared variance, which is going to push the weights from the different models to be the same. They can have the same sparsity level. So select around the same, like 20% of the features, but they can be very different features across the different models. Or we can force the same features across the tasks. And that could also be like a very sparse level. And so this is what it looks like. So instead of having this big distribution where I pool everything together and hope that for the best, it's going to like actually behave like a single distribution, then in this case, I say that I have different distributions, and I build a model, and then this model is actually constrained to look like the other models that come out from the different distributions. And this is an optimization process that goes back to the different models, a bit like the MKL did earlier. And if we look at the result from there, so we see, as I was saying, the results, like just the overall results are quite weak. It is hard to see a correlation there, but this is a correlation between the targets and the predictions. If you don't correct, if you correct with a GLM, and then if you apply the multitask learning scheme. And I think it's better here, where you see this is the R squared for like those three models. So no correction, correction, and multitask learning, and the mean squared error. And we can also look at the different, so one important point is here that those, because they assume a single distribution, they're just concatenated across all of the different groups. And multitask, what it does instead is it averages across the different groups. So they're not the exact same metrics. I do have the numbers for the exact same metrics as well. It's just here it represents what people do in practice, like how we would use, if I ask you to use an SVM on this task, what metrics you would come out with. But the last thing that was interesting is to also look at the similarity, again, the cosine similarity between the different methods. So we have here that there's actually a fairly good agreement between the corrected and uncorrected models. Now, if we take all of those tasks separately without imposing that they, oh, sorry. Oh, how can I go back? Okay. Without imposing that they share anything, then we see that basically things are very different here. And we obtain models that are very different. And that's because they're going to fit the noise within their distribution. Now, on the opposite, if I impose that they share something, we actually have weights that are very close to one another, but also they're very close to the uncorrected and corrected models. So they have learned something that resembles this unique distribution, but it's not exactly the same as the results show. So we think this technique could potentially be a nice way to deal with at least categorical confounds, because it does not make that single distribution assumption. And also, what is nice about it is that the implementation is easy, because what you do is you start with your models as being completely separate, and then there's actually a really nice implementation of multitask learning by Carlos Li觥, which has done it in the kernel, so in the primal, in the dual, so that it's actually very efficient. And it works well with neuroimaging data, which is not the case for the primal formulations. And that also is going to kind of take care of those things like permutations, because permutations are going to happen naturally within each of those subgroups as well. So you're going to have like a better controlled model when you're doing that. But of course, it has limitations. The smaller subgroup defines the cross-validation scheme. If you have confounds that lead to very tiny groups in the end, this is going to be hard to actually do cross-validation on that. If you do have a tiny subgroup, and then you average the results across the subgroups, like is done for multitask learning, you can artificially inflate your results, because if you have some population that is very small, you can obtain artificially high correlation value. And you need to make another assumption, which is how the tasks are related. Now, I tested a couple, and they showed very similar results, and including an implementation that actually learns how the tasks are related. And you can actually look afterwards at the covariance between the tasks, which is nice, because it really shows if there are some tasks that are like more structured or more clustered together, or if you should really consider them like as separate things. But it is another assumption. And you also need to define your confounds. So whether when you define your groups, then it's really going to kind of forget about them. So if you say that gender is a group and you have very different patterns within each of the groups, then you might end up with forcing the model to generalize across men and women while it should not, and it should give you different patterns. Now, a pretty nice way to actually look at that would be to build the single models as well and compare the single models for men and women and the multitask version that imposes that they share the same weight representation, and see how they perform and see how they compare and what the patterns look like, because that could give a hint on whether or not it would be interesting to look at this confound, like at this what we consider the confound as a potential source of signal as well. So to kind of wrap up on this, basically, be careful when using machine learning for models for discovery. It's, as we've seen, like the using and relying on weight patterns can be dangerous. So, like, do you really need machine learning? Is it really answering your question? Machine learning is aimed at making predictions. Do you care about those predictions? Well, if not, maybe you shouldn't look at machine learning models. Before you do, make sure you assess the characteristics of your data as much as possible so that you can maybe make the better assumptions. Try different techniques if you are using it for discovery. Complement it with other techniques to make sure that things correlate, especially if you're looking at classification. You have pattern A versus pattern B, and sometimes you think that the model is actually showing you something and is relying on pattern A, but is actually finding signals for pattern B, which can be just noise, and it does happen. So this is also important to look at a variety of techniques and acknowledge all of your assumptions as well. So we make more assumptions than we tend to think of, and it is very important to try and really identify all of them and to think whether they actually match the signals that we have. So all of this work actually was implemented in Pronto. This is the pattern recognition for neuroimaging toolbox. As you can see, I've been a fairly consistent contributor over the years, but now it's over. And actually, we're going to have, so it's an open source toolbox written in MATLAB. I don't know who uses MATLAB still? Or, okay, so still quite a fair amount. And version 3 is going to come out. I mean, I'm not really like making decisions anymore, but hopefully sometime next month. And in that one, you'll have MKL where you can apply it across different modalities. And that means we also have implemented support for SPM MEG objects and .mat files. So you'll be able to perform MKL, so build one kernel per modality, and then combine them in a sparse way to actually see which modality has the most information for your signal, or if they are correlated or not, and things like that. And we also have a couple of primal formulations because we have support for .mat. So if you are extracting features, so doing some feature engineering, like getting the volume in a brain area instead of like voxel-wise, we also have primal formulations with different regularizations as well. And there are actually quite a few new things as well coming, but And I actually forgot to put the link, I think, but just, yeah, if you look for Pronto and then my name, it should come up. If you look for just Pronto, you'll probably be suggested to order pizza from somewhere, but which might be better, but you know. So this is what it looks like. We have different interfaces. We have some like push buttons, but we also have the SPM batch system for those who are familiar with that. It allows to do some more efficient computations and to actually launch stuff on the cloud, or like your high-performance computing system as well. So you can automatize a bit the analyses, and then you get, well, not really fancy, but just like okay plots, I guess. And yeah, so I want to acknowledge the people who helped me through like all that work, and that's mostly Janina Moiro-Miranda and all her team at UCL, also people from the ParVD lab at Stanford, the Pronto team, which is larger, and also like money. So I don't know how much, I have no idea how much time I still have.
I think we have some questions. Maybe during the questions we can try to see if we can do this. But if you have questions for the speaker. So I'll have one. So you make a case about potentially not using machine learning for discovery, but can you think of counterexamples and places where it can really help? Or you just, that's only for prediction?
So I think it's better suited for predictions. The thing is, the problem is, if you run an SPM, if you run other techniques, univariate techniques, or even you run a searchlight, and because it's not capturing long distance dependencies, you might not see a signal. So I think if you want to show that there is signal there, you can use it to look at model performance. Now, if you want to then look at the weights, you can look at the weights, but you have to be aware that it is not a direct relationship. And so maybe there will be some voxels or brain areas that will be related to your signal of interest. If you are not finding it in an SPM, it's probably a quite weak signal. But also you will have regions or voxels that are in there and even in the top contributions because of noise cancellation, especially if your effect is low signal to noise ratio. So it just needs more investigation. It needs to be, yeah, you need to be very careful about just saying, oh, I have significant classification on this problem where we couldn't find any results on SPM, and I've reviewed many papers like that, and I've probably written some as well, just saying that. So we can't get an SPM on this. We're doing machine learning. We have significant classification accuracy. That's awesome. It means that there's signal, and we look at the weight maps, and the signal is there, there, and there. But there's actually more to that story, and I think it's really the main message here, that it is not as simple as that.
Models to account for confounding signals. Apart from, obviously there's an arbitrarily large number of potential confounding effects that one might account for. Apart from losing degrees of freedom that way, are there any other problems? If I just go around and try all possible combinations of confounds that I could possibly account for and rerun my machine learning analysis, is there a limit to how many confounds I could possibly
You mean with using the GLM strategy?
Well, I mean, obviously it can be done. I'm thinking more about how to account for the multiplicity of models that I've tried on my data.
And wait, I'm sorry. Are you talking about the GLM or the multitask learning?
I'm talking about the GLM modeling of confounding factors. Is there a limit to how many confounds it can be?
No, there is none. You might just, yeah, as I mentioned, like lose signal. And also the thing is, if you're doing that, you need to take into account the stratification into all of the aspects of your analysis. And I didn't really mention it, but cross-validation would be one on top of the permutations that I mentioned. But cross-validation would be another one where you would want to also make sure that cross-validation is balanced across the different groups in terms of the targets as well. But that's something that's actually typically done. So in terms of when you have confounds, researchers tend to actually balance their cross-validation folds, but then they completely forget about it as soon as they reach the final results, and then they want to assess performance, like significance on that, and they run permutations, and they completely forget about the stratification. So the thing is to really take into account that stratification across all of the steps of the analysis.
Maybe just one more, if I may. You said in your introduction that we're nowhere near having classification algorithms that have diagnostic value. Yes, there are 1,000 papers out there that all claim to find positive results. I was wondering, what is, in your opinion, the main reason that there aren't any diagnostic applications for fMRI?
Well, I think for fMRI specifically, or like any type?
You can expand it too.
But I think like the first thing with fMRI is it's a very small data sets is one. There is an improvement in the size of the data sets and the sharing of data sets, but then you have confounds based on like which scanner, which sites, or which countries things were recorded in. It's something we see in general in health. Like data is just very heterogeneous. It is hard to build a very robust system. And as soon as you push the systems a bit, even in some of the studies, and they do find the limitations quite quickly. So actually having something deployed in the hospitals in the way that is published now, I think would be quite dangerous. There are also another number of considerations we would need to take into account. That means the fairness of the model, how transparent we are, how can we assess domain shift, how can we make sure that a new test point is in the distribution of our training set, for example. All these things have actually been very little addressed, especially and that's in health in general. There are efforts, there are fairly recent efforts, but there are efforts in that direction. But especially for brain imaging, the size of the data set, I think, has been the major barrier. But even when that is lifted, there's still a lot to catch up with, like the more recent techniques and all of the different aspects of the machine learning model, because performance is like, that's another thing, metrics. If you look at the whole like area under the curve, that is not clinically feasible. You can only look at a very small part of that area under the curve for a clinically feasible deployment. But once you're there, you haven't optimized for that. So you need to rethink about your metric, and maybe you should optimize for something that would be in your clinically feasible range. So there are like a whole number of extra steps we would need to take, and that's why we're really that's also why I see those works as preliminary steps towards that direction, and which is why I don't think we're there yet.
Anybody else? Well, let's thank our speaker again.
Okay. try a couple more slides if you have time or if we have the room, but. Yeah, so just like as Javier mentioned, I'm not in academia anymore. I'm at Google Health now. Does that mean that I can forget about all this? Well, no. I wished. But we have the exact same problem. Now, I do have another presentation on the work that I'm doing at Google and what Google Health is actually doing in the medical domain, but I don't think it's going to work. But I can just say, like, in general, there are teams at Google Brain that have been looking at diabetic retinopathy to detect the damage in the eyes from diabetes, and they have systems that are being tested for deployment in Thailand and in India, where the resources for screening those images are very low. There are also projects with detecting eye diseases and the urgency of those diseases, because the clinical system, especially in the UK, is completely overloaded because so it's free. So it just, you know, everyone walks in and it's free, which means that their just waits are very long. Doctors are completely overwhelmed, and so there is this project to like really help assess which cases are more urgent to prioritize better, and they've shown that they're actually on par with eye experts. And their model has a really nice illustration in how it produces a 3D segmentation, which could help with interpretability as well. Then the project that I'm working on is actually, so I'm working a little bit on the eye thing, but I'm mostly working with electronic health records. So when you go to the hospital, there is like an admission process, and then they take a blood sample, and the labs get all recorded, and then you have vitals, and so you have a whole like patient timeline. And in that case, the goal was to predict when a patient would have a high risk of developing an acute kidney injury within the next 48 hours. So it was really prognosis, not diagnosis. The event had not happened yet, but it was really to say, okay, like this patient, if you continue with that treatment, or if the patient continues on being dehydrated, they're going to get acute kidney injury. And so that's, now there's a whole problem with causality in that case, because we're assessing and predicting something that has not happened yet. And we need to make sure that it's not interpreted as causal, because it's a correlation. Our model is a correlation model, as all machine learning models are, like the ones I talked about, at least. Yeah, we're also looking at all those like number of steps that, and really investigating so that these technologies can be put out there for those cases. So yeah, so I can't forget about all of this, because interpretability and confounding factors happen in all those data sets that I'm actually still looking at right now. And I have a whole different set of slides for how this applies to deep learning techniques. And it's, yeah, even trickier in some cases, especially in the interpretability part. Yeah, do you have questions about Google Health? Yep.
You mentioned fairness and confounding algorithms. What is your sense of the role they think? How will they fit into that? Closed source,
Yeah, so I mean, for sure, it's yeah, I guess there's still like I'm not necessarily aware of like what is the long-term plan for like Google Health in general in terms of how they're going to open source the models or not. I don't think they would open source the models, but they do open source at least part of the code, and they publish, which means that you could replicate that. Now, I think the very important part is that the users understand what is going on, and how we built the model and how the model could be used. And we also need to factor in how they will use the model. So if you have a system with a lot of false positives, they're just going to snooze the alarm. And that actually has been shown in the past, but that's going to create a bias in how your patients are treated. And this is especially if your model is not very fair from the start, you have more false positives for a specific group, then they're going to snooze the alarms always for that group, and it's going to affect that group way more. So all like this issue of fairness and robustness and transparency, they're taken very seriously because there is a lot of tension, and like these are first steps, and if those first steps are not done like very properly, the medical institutions will have they already have a lot of reticence towards tech, and especially towards tech companies, but just towards AI in general. And so if we don't provide those steps in a very thorough way, then it would expose like a really like a not just a backlash for the company, but also just for health in general, because it would mean that those systems and other research could not get out there.
We're going to have to leave the room, but if anybody has more questions or want to hear more about her job, her work at Google Health, you can either join us for lunch or you can send me an email. We'll be going out for dinner at 6 p.m. So just send me an email and you can continue the conversation. Thank you.
Thank you.